I want to use this opportunity to compare some different technologies and see what lessons from the past we can apply to the future superconnecting supercomputers that you folks are building.
Ready for a deep dive. Today, we're taking a look at supercomputing, more specifically, superconducting supercomputers, and, how we might learn a thing or two from the VLSI era to help build them.
It really is something how tech from way back when can help us push the limits like we're doing with superconductors these days.
Totally. Like finding some old tool in your dad's workshop that's perfect for, I don't know, fixing a spaceship or something. But to get where we're going, got to start with the basics, right? CMOS, it's everywhere in electronics. But here's the kicker. It's not all ones and zeros.
Yeah, there's this wild thing in CMS, the X state. It's almost like the computer needs a second to figure out if a signal is a 1 or a 0, like a little digital crisis.
Hold on, X state. Sounds like it could cause some serious issues if a computer can't tell its ones from its zeros. What happens then?
You're right on the money there. It all comes down to reliability. CMOS uses different voltages for informations, high voltage for 1, low for 0. But there's always a bit of noise, fluctuations. The X state is basically the circuit going, hang on, is this for real or just a blip?
So like when you're texting with a bad signal and the message gets all jumbled, that moment of, wait, did they just ask me to pick up a singing frog on the way home?
Exactly. And just like you don't want a messed up text leading to a weird shopping trip, we definitely don't want a supercomputer getting confused because of signal noise. That's where this X state comes in. Helps keep things reliable, especially as we try to make things faster and faster.
Makes sense. Now, the stuff we sent, you also mentioned something called gain with CMOS. Is that like turning up the volume on the signal to make it clearer?
You got it. Gain is all about making that signal stronger. Higher gain usually means it's better at ignoring the noise. Picture a graph. Input voltage on one side, output on the other. A steep line means high gain. A small change in the input makes a big difference in the output. Easier to tell your zeros from your ones.
So if I'm picturing this right, a steep line, almost straight up, that's like a super clear signal, high gain. But a more gradual line means the signal's weaker, more likely to get lost in the noise, so lower gain.
You got it. But here's the thing, you can't just max out the gain and call it a day. It's a balancing act. Too much gain, and you run into other design problems.
So it's got to be just right, like finding the right setting on your stereo, too much bass, and the neighbors complain, but not enough, and you're missing out on all the good stuff.
Exactly. It's all about finding that sweet spot for the gain to get the circuit running at its best. And speaking of finding the right balance, let's move on to how those signals actually move around a chip.
Because I'm guessing those tiny wires aren't exactly like, super fast highways, right?
Yeah, more like those back roads where you're lucky to go 10 miles an hour.
Well, the electron's moving a little faster than that, but you get the idea. These tiny little wires, they act like, transmission lines, especially when they get longer. Just like those big power lines you see, they've got resistance and capacitance.
Wait, capacitance? Like from physics class?
Oh.
Something about storing energy, right? What's that got to do with super fast superconductors?
Yeah, got it. Capacitance is like a little energy store. And in these tiny wires, it means the signal takes its time, doesn't just zip through instantly. It's more like sending a light pulse down a fiber optic cable. The further it goes, the weaker, the fuzzier it gets.
So instead of a clean on or off right when you expect it, you get this, delayed message, all blurry at the other end.
Yes.
Sounds like a recipe for disaster with your data. Exactly. It's a telephone game. But instead of mishearing a word, you get a critical error. And this distortion, it's even worse with how fast superconducting circuits are. It's like trying to watch, a movie on a flickering old TV.
Yeah, no thanks. So how do engineers even start to fix that? Can you even fix it? Or are we stuck with laggy supercomputers?
Don't worry, we're not doomed to a life of buffering. This is where those fancy design tools come in. Engineers need software, powerful stuff that can figure out these transmission line effects. Got to get ahead of those distortions before they even happen.
So it's like, a super GPS for your electrons, making sure they all show up at the right spot, on time.
That's a great way to put it. And this kind of leads us to something else we got to talk about, metastability.
Metastability. Okay, that sounds kind of scary, like the computer's about to self-destruct. What's going on there?
It's not quite a digital meltdown, but it's definitely a pain. Metastability, it's when a register, think of it as a tiny memory cell, can't decide, 0 or 1. It gets stuck.
So instead of making a choice, it's stuck on maybe.
Exactly. And the faster you try to run things, the more often you hit this problem. It's like, flipping a coin super fast. Every so often, it's going to land on its side, right? That tiny moment of, ooh, who knows, can really mess up your calculations.
The stuff we sent you had this analogy, a ping pong ball balanced on a hill. Can you explain that?
Yeah, it's perfect. Picture this, a ping pong ball at the very tippy top of a hill. Which way will it roll? Could go either way, right?
Yeah.
And it might just sit there for a bit before it decides. That's metastability in a nutshell.
So it's like computer indecision, but with, well, disastrous results. These circuits are more high maintenance than I thought.
They can be a bit finicky, but hey, engineers are clever. There are ways around it. One surprisingly simple fix is using two registers, one after the other. It's like giving the signal a bit of extra time to figure itself out, to settle on 0 or 1. Cuts down the chances of metastability messing things up.
So like double saving an important document just to be sure.
Exactly. Yeah. Might seem kind of pointless, but when you're dealing with these crazy fast speeds, that little bit extra can make all the difference. Means a working supercomputer, not a very expensive paperweight.
Good to know their solutions. But let's get to the time travel part. How does looking back at those old VLSI problems help us build better superconducting supercomputers now?
It's all about understanding what let engineers build complex stuff back then. They had limited tools, In the early days of VLSI, they used these things called generators.
Generators, like the gas-powered kind. What do those have to do with the chips? Not quite those kinds of generators. Think of them more like design helpers, especially for making those repeating patterns you see in circuits.
Yeah, exactly. Back then, no fancy software to just drag and drop every transistor. They used these generators to make big chunks of a circuit, pre-designed to do a specific job. It's like using a stamp to make a big, intricate design.
So instead of drawing everything by hand, they had reusable templates for the common stuff. Pretty clever. So how does that help us with our superconducting future?
That's the really cool part, this whole idea of using regular modular designs. Could be even more important for superconducting computers. Remember how sensitive these circuits are. Having those repeating patterns, it could be how we manage that complexity. Make big, reliable systems.
Like building a skyscraper, right?
Yeah.
Neat stacks of bricks are going to be a lot more stable than just like piling up random rocks.
Perfect analogy.
Yeah.
And a really neat example of this whole generator thing from VLSI, it's called a programmable logic array, PLA.
PLA. Okay. Sounds interesting. What did those actually look like? How did they work?
So imagine a grid, like a huge spreadsheet. Every cell you can turn it on or off, and by carefully setting specific cells, you could actually physically make a logic equation.
So you're building circuits just by arranging transistors on a grid, like those old pegboards, and you put the colored pegs in to make a design. That was the PLA.
That's it. Now, the tech to build them, it's totally different for superconducting stuff, but the idea is the same. Regular modular. Could be huge for dealing with how complex and how big we want these new systems to be.
It's kind of mind-blowing, We're looking at solutions to these super advanced problems, and the answers might be in designs from when engineers were still using pencils to make the first computer chips.
It just shows you. Sometimes the best ideas come from looking at the past in a new way. VLSI might be old news, but it's got all this knowledge that could change how we think about supercomputing.
Good reminder that progress, it's not always a straight line, huh? Sometimes to go forward, gotta take a detour to the past. And on that note, gotta wrap up this deep dive, folks. Thanks for joining us.